this video, we will be optimizing the shape of a wing to reach maximum lift over drag ratio. To do so, we could obviously set up a large number of parameters, try different design, and run all the design point and see which design is the best. What we wanted to do in this video, however, is to show you how the Adjoint solver technology can actually automatically optimize the shape of this wing to reach maximum lift over drag ratio. And actually, before we start, here's a little spoiler. On the left, the initial geometry with a lift over drag ratio of 12, and on the right, the optimized geometry with a lift over drag ratio of 60. So let's see how we got that done. Now here is our geometry with the wing in the center and the rest being the air domain. We can see the inlet, and here is the outlet. Now that was a simulation that was already run with the initial wing shape actually, so we can actually zoom in a little bit and see the wing, and what you're looking at right now are the velocity contour. Obviously it's non-symmetric because there is a wind angle or an airflow angle of 1.5 degrees when compared to the wind chord. And here is another view with the pressure field. So again, that's our initial condition. Now we will be using the Adjoint solver. We'll see how to define the observables, define the controls, monitor the Adjoint solver simulation, and actually how to run the Adjoint solver. Creating the observable, which is the ratio of the lift force over the drag force. So I actually select an operation type, which is again the ratio, give it a name. We're going to call it ratio lift over drag very easily. We're going to pick up the numerator, which is the force lift, and the denominator, which is the drag force. And here we have our observable, which again we want to maximize the ratio. I already ran the Adjoint solver in the background, and I'm ready to optimize the shape of the wing. The first thing I'm going to do is look at the current lift over drag ratio, which is 12.11. And now that I know where I start off, I'm going to actually go in the mesh morphing tool, and I already defined the box where I want mesh morphing to occur. I'm gonna select the surfaces of the wing to say that that's the geometry we want to change. I'm gonna update everything, and because I already ran the Adjoint solver, I can know the expected change of the new shape, 1.85 of better lift over drag ratio. I can modify the mesh, just check that the modification is acceptable. I accept it, and you will not see it on the screen, but the shape was actually modified and the mesh morphed. Of course, because I just changed the shape, I have to recompute the CFD calculation, which I'm doing right now. The simulation with the new shape is completed, so what I can do is evaluate the observable as we did before, and now my lift over drag ratio is 13.97. Let's take a look at what we did. We actually had an initial shape where the lift over drag ratio was 12.11. We ran the Adjoint solver, and it predicted an improvement of this ratio of 1.85. So knowing that, we actually modify the shape, we do the mesh morphing, we redo the CFD calculation, we evaluate the lift over drag ratio, and we found that the new value is 13.97. Actually an error of in the prediction of 0.07%, which is very good. And of course we can run the Adjoint solver again. The new improvement prediction would be 1.78. And we would do the same process again and again till the best performance is achieved. Obviously, we're not going to do that manually. We can use very simple script to automate the entire process. And even if you do only a few iterations of the adjoint solver, you can already see how the initial shape was modified to give a new shape with a better lift over drag ratio. You can easily take a look at that into CFD pose, for example, and compare the two designs at the same time. Please visit ansys.com for more information about the adjoint solver and a step-by-step tutorial.